In this video, I want to explain why this property is true for when the variables are real and all expressions we calculate the values on the left and right hand side are real. And I'll be explaining this for positive integer, negative integer, zero, rational, and irrational exponents. 5 cubed and that to the 4th power. Based on definition of exponential repeating multiplication, we get this. 5 cubed multiplied to itself 4 times. Again, we use the definition of exponential repeating multiplication, and we get this. 5 cubed is equal to 5 times 5 times 5. 5 multiplied to itself 3 times. In each of these, we have 3 5s. So how many 5s do we have in total? 3 plus 3 plus 3 plus 3. And that will be repeating addition, which is definition of multiplication. And so that would be 4 times 3. And so we have 4 times 3 5s. And so we get the total to be 5 to the 4 times 3. And based on the commutative property of multiplication, that is 5 to the 3 times 4. And so we are multiplying these exponents. And you can do likewise with variables. 5 to the negative 3 and that to the 4th power. Well, based on a property that I said later in the set of videos, 5 to the negative 3 is equal to 1 over 5 cubed. Now, based on property that I already explained in the set of videos, we can distribute the 4th power to both the numerator and denominator and get this. Now, 1 to the 4th power, that is 1, and we just learned that 5 cubed and that to the 4th power is equal to 5 to the 3 times 4. Now, again, we use the property that I explained later in the set of videos. And now, negative parentheses 3 times 4 is equal to negative 3 and that times 4. And likewise with variables, and you can do the case of where you have first a positive exponent and then a negative exponent, and then likewise with variables, and then you can do the case of both being negative exponents, and to the left is one way to show why that works, and to the right is another way to show why that works, and likewise with variables. 5 to the 0th power and that to the 4th power. Well, as I explained later in the set of videos, anything but 0 and that to the 0th power is equal to 1. Now 1 to the 4th power, that is equal to 1. And again, we use the property that anything but 0 to the 0th power is equal to 1. And so we get that to be equal to 5 to the 0. And 0 is equal to 0 times 4. And so we get this. And likewise with variables, for this case of at least the first exponent to be 0. And here's a case of at least the second exponent to be 0. Likewise with variables. In both of those cases included the possibility of both of the exponents being 0. We still can talk about this case separately, and then likewise with variables. The non-calculus definition for when the exponent is 1/3. A to the 1/3 and a cubed are inverses. So that means that a to the 1/3 and that cubed is equal to a. And that also means that a cubed and that to the 1/3 is equal to a. And likewise with d being a variable, and this non-calculus definition is at least 4, where d is a positive integer, which is all we need to know for this video. Let's let this expression be equal to y. Now let's take both sides to the 7th power, and we get this because going to the 1/7 power and going to the 7th power, those are inverses. Now let's cube both sides, and we get this because going to the 1/3 power and cubing, those are inverses. Now we already know the property that we're trying to prove in this video already works for integer exponents, and so we get this. Now 7 times 3 is equal to 21. And now let's take both sides to the 1/21st power, and we get this because going to the 1/21st power and going to the 21st power, those are inverses. And now using the first line, we get this. And likewise with variables. However, we have different last two steps because dg could be even, so all we know is that the absolute values are equal. That means that the left side is equal to the right side or the negative of the right side without the absolute values. And we want to show that it is a former for when all the expressions and all the values are real. And let's do that by going through each real case. If a is positive and all expressions are real, then that is positive, and that is positive. So without the absolute values, the left and right hand side are positive, and so the left and right hand side are equal. If a is negative and all expressions are real, then that is negative, and that is negative. So without the absolute values, the left and right hand side are negative, and so the left and right hand side are equal without the absolute values. If a is 0 and all expressions are real, then that is 0, and that is 0. And so we have the left and right hand side to be 0 without the absolute values, and so we know they're equal without the absolute values. 5 to the 1/3. that squared, and that cubed. We already know that this property that we're trying to prove this video, we already know it works for integer exponents, and so we have this. Now based on the commutative property of multiplication, we have this. 2 times 3 is equal to 3 times 2. And again, we use the idea that this property that we're trying to prove in this video, it already works for integer exponents, and so we have this. Now going to the 1/3 power and cubing, those are inverses, and so we have this. Therefore, these two expressions are equal. Let's take both sides to the 1/3 power, and we have this. And now cubing and going to the 1/3 power, those are inverses, and so we get this. And likewise with variables. However, the last two lines are a bit different because d could be even. All we know right now is that the absolute values are equal. So that means that the left-hand side is equal to the right-hand side or the negative of the right-hand side without the absolute values. We want to show it is the former for all cases where all the values are real and all expressions to figure out the left and right-hand side are real. So let's go through each case. If A is positive and all expressions are real, then that is positive, that is positive, that is positive, and that is positive. So that means that without the absolute values, the left and right hand side are positive, and because both of them are positive, that means that without the absolute values, the left and right hand side are equal. If C is even and all expressions are real, then that is positive, and that is positive, and so that means without the absolute values, the left and right hand side are positive, and because both of them are positive, they are equal without the absolute values. If A is negative, C is odd, and all expressions are real, and that is negative, that is negative, that is negative, and that is negative. So without the absolute values, the left and right hand side are negative, and because they would be both negative, that means without the absolute values, the left and right hand side are equal. If A is equal to 0 and all expressions are real, then that is 0, that is 0, that is 0, and that is 0. Because 0 is equal to 0, that means without the absolute values, the left and right hand side are equal. The non-calculus definition of fractional exponents where the numerator does not have to be 1 is this. So for example, 64 to the 2/3 is equal to 64 to the 1/3 and that squared. Now 64 to the 1/3 is equal to 4 and 4 squared is equal to 16. This definition is at least for C as a positive integer that is not 1, but you can show that this equation works for other real cases as well if that's not actually the non-calculus definition for those cases. And here's the explanation for those cases with C as an integer and D as a positive integer, which are the cases we need to know for this video. And first we do the case of C is equal to 1 and it works. And then we do it for the case of C is equal to 0. Now 0 over D is equal to 0. And anything but 0 and that to the 0, that is equal to 1, as I explained later in the set of videos. And again, we use that property. If C is a negative integer, we know this, as explained later in the set of videos. That's a future property in the set of videos. And then we use a non-calculus definition of fractional exponents. And again, we use that property of negative exponents that I explained later in the set of videos. 5 to the 2/3, and that to the 4/7. Based on the previous slide, we get this. And now based on the previous slides before that slide, we know we can switch the 2 and the 1/7. And we get this. Now based on the previous slides before those, we know we can have going to the 1/3 and going to the 1/7 as going to the 1 over 3 times 7. And we already know way earlier in this video that this property that we're trying to prove in this video, we already know it works for when you have integer exponents. And again, we use that previous slide. And we have this. Now to multiply fractions, you multiply both the numerators and the denominators, and we sort of undo the multiplying of the fractions, and we get this. And you can do likewise with variables. 5 to the pi, and that to the e. If you punch that into your calculator, you get this. 5 to the 3 times 3, we get this. As you get closer and closer and closer to the left-hand side being 5 to the pi e, the right-hand side becomes closer and closer and closer to 931146.61, and so on. And so it makes sense for 5 to the pi e to be equal to 5 to the pi and that to the e. Thank you for watching this video. Here is the link for the playlist about the why behind for some properties of exponents.